Welcome to the DIY Honda Garage channel. The DTC P16E3 indicates a communication error between the powertrain control module, PCM, and the battery sensor. This problem pertains to the battery sensor LIN, or Local Interconnect Network, which serves as a communication tool within the vehicle system. The battery sensor's main role is to monitor the voltage and current of the vehicle's 12-volt battery, providing vital information to the PCM for optimizing engine performance. The sensor is typically located near the battery terminal, connected via a 2-pin 2P connector. Proper operation of the battery sensor is essential for the vehicle's electronics and overall function, as the PCM relies on the data to manage various aspects of vehicle performance, such as fuel efficiency and emissions control. If there is a communication error, it could result in multiple system malfunctions, requiring precise troubleshooting to identify and rectify the failure. The DTC P16E3 reflects a problem specifically with the battery sensor LIN communication, which is a typical concern in Honda Civic models from 2016 to 2021. This sensor is crucial for monitoring various battery parameters and communicating with the PCM to ensure optimal vehicle operation. When this communication fails, it can lead to incorrect readings and potentially affect the overall vehicle performance. The sensor is physically located at the battery terminal, connected through a 2-pin connector, facilitating its communication with the vehicle's onboard systems. If this link is compromised, the battery sensor is unable to relay critical information, risking battery mismanagement, which could lead to starting problems or electrical system malfunctions. Understanding the possible causes for DTC P16E3 can help in troubleshooting the issue efficiently. First, loose terminals at the 12-volt battery sensor can disrupt communication signals to the PCM, indicating a potential area for concern. Second, if the local interconnect network wire, LIN wire, is shorted somewhere along its path, it can cause erroneous signals and trigger the communication error. Third, an open wire in the communication line can prevent effective communication between the battery sensor and the PCM, rendering the sensor ineffective. Each of these issues requires careful inspection and testing to ensure a complete resolution of the error. The symptoms associated with DTC P16E3 can manifest in various ways, primarily through error codes appearing on the diagnostic tools used by technicians. Drivers may also notice battery-related performance issues, such as the vehicle struggling to start or experiencing electrical malfunctions. Additionally, the vehicle's onboard diagnostic system might alert the driver to issues relating to the battery or charging system. These symptoms highlight the necessity for timely diagnosis and repair to prevent further complications in vehicle operation and ensure the reliability of the electrical system. In the first troubleshooting step for DTC P16E3, it's essential to turn the vehicle's ignition to the on mode to initialize the diagnostic system. By using the Honda Diagnostic System, HDS, to clear any existing DTCs, you allow the vehicle to reset, making it easier to detect ongoing issues. Waiting for approximately 5 seconds allows the vehicle's onboard systems to fully process the reset. Once this time has elapsed, checking for both pending and confirmed DTCs will determine if the issue persists. If DTC P16E3 reappears, the failure can be categorized as persistent. Conversely, if it does not, the problem may be intermittent, prompting further investigation into terminal connections and wiring. Step 2 involves rechecking for pending and confirmed DTCs using the Honda Diagnostic System, HDS. This helps verify if the previously noted DTC P16E3 still exists, or if any new error codes have emerged, which can provide further insights into the vehicle's issue. If DTC P16E3 indicating a different LIN communication error is present, you will need to proceed to the next troubleshooting step that involves further diagnostic measures. However, if P16E3 is absent, you might be dealing with a different issue that requires checking for loose connections at the battery sensor and the PCM. Proper attention to these details is vital to ensure a thorough troubleshooting process. To proceed with troubleshooting in Step 3, first power off the vehicle by turning the key to the off lock position. Next, you will disconnect the 2P connector of the 12-volt battery sensor to isolate the sensor from the circuit. Once disconnected, it is crucial to check for continuity between designated test points in the circuit to ensure proper connectivity. The vehicle should be in the off mode during this check to avoid any electrical interference. Testing these points will help identify if there are any breaks or faults in the wiring, leading to the communication error. Continuity checking is fundamental here and can elucidate whether the issue lies within the battery sensor itself or in the wiring leading to it. In Step 4, you will need to initiate a CS short with the HDS and allow it to sit for more than 1 minute. This action prepares the circuit for an in-depth continuity check. Following this, check for continuity between the 12-volt battery sensor's terminals and body ground by disconnecting connectors from the alternator and PCM one at a time. Monitoring changes in continuity while disconnecting helps isolate the location of the short or fault. If disconnecting one of the connectors results in loss of continuity, the LIN bat sensor or LIN wire is likely functioning correctly, suggesting that another component may be at fault. If there remains continuity, the next step will involve addressing wiring issues directly. Step 5 requires you to reconnect the 2P connector for the 12-volt battery sensor to ensure it is actively communicating with the system. Next, disconnect the alternator's 1P connector to begin a continuity check between the two specified points. This step helps establish whether the issue lies within the alternator or the battery sensor itself. By monitoring for continuity while the vehicle is off, you determine if the battery sensor is receiving adequate signals to function correctly. If continuity exists during this test, the diagnosis will lead to replacing the battery sensor. If not, you will proceed to further troubleshoot with other components involved. In the 6th step of troubleshooting for DTC P16E3, once again jump the SCS line using the HDS and wait for more than 1 minute. After this, disconnect both the 12-volt battery sensor's 2P connector and the PCM's A connector to prepare for a continuity check. Ensuring that the wiring is disconnected allows for a clear assessment of the communication line without interference. If continuity exists between the specified test points while the vehicle is off, you can conclude that the LIN at sensor wire is functioning properly. If there's no continuity, this indicates a potential break or open in the LIN wire, necessitating repairs along the communication route to restore proper function. Step 7 involves checking the integrity of fuse A24, which is a 10A fuse located in the underhood fuse/relay box. This fuse plays a key role in protecting circuits associated with the battery sensor and must be in good condition for the system to operate correctly. If the fuse is intact, you will proceed to Step 8. However, if the fuse is blown or damaged, it points to a short circuit in the +B horn wire that leads from the battery sensor to the fuse. This short circuit must be repaired before replacing the fuse to ensure a long-term fix for the communication error. Proper fuse function is critical to maintaining the operation of the vehicle's critical systems. In troubleshooting Step 8, your first action is to disconnect the 12-volt battery sensor's 2P connector. After disconnecting, you will measure the voltage across the designated test points in order to see if battery voltage is present. This check should occur with the vehicle off to provide accurate readings and ensure no active electrical flow interferes with the measurements. If you find that voltage is present, it indicates that the +B horn wire is functioning correctly. However, if there's no battery voltage present at this point, investigate the +B horn wire for any opens between the sensor and fuse A24. Identifying and repairing this open wire will help resolve the communication issue effectively. Finalizing the troubleshooting process in Step 9 entails first jumping the SCS line with the HDS once again and holding it for over a minute. Following this protocol, disconnect the PCM connector A50P to isolate the PCM from circuits. This helps ensure an accurate continuity check between the battery sensor and the PCM. Testing the continuity will reveal if the LIN BAT sensor wire is functioning correctly. If continuity is confirmed, it likely indicates that the battery sensor itself requires replacement. Conversely, if continuity does not exist, it points to an open in the LIN wire, requiring targeted repairs. Once all troubleshooting steps for DTC P16E3 have been followed and necessary repairs have been made, it's essential to perform a final verification. Begin by clearing all DTCs using the HDS. After clearing the codes, initiate a thorough test drive of the vehicle to ensure that all systems operate correctly, without error codes being triggered again. This testing phase is critical to confirm whether the repairs effectively address the issue or if further investigation is still required. The objective is to validate that the DTC no longer reappears, indicating that the root problem has been successfully resolved. Continuous monitoring of the vehicle might reveal additional inconsistencies that should also be addressed. Preventive maintenance is crucial for avoiding issues related to DTC P16E3 in the future. Regularly inspecting and securing all connections related to the 12-volt battery sensor will help prevent loose terminals that could disrupt communication. Additionally, performing routine maintenance on the battery itself, including cleaning terminals and ensuring proper charge levels, contributes to the longevity and performance of the battery and its associated systems. Lastly, it's important to stay vigilant and monitor for any alerts or diagnostic messages your vehicle may produce. Proactive steps like these can significantly reduce the likelihood of encountering similar communication errors in the future, ensuring uninterrupted vehicle performance. In conclusion, DTC P16E3 signifies a communication error that can have various underlying causes, primarily originating from wiring faults or loose connections at the battery sensor. A systematic approach to troubleshooting, as outlined, is vital for identifying the specific issue. Each troubleshooting step is designed to progressively eliminate possible faults until the root cause is identified and resolved. Corrective actions, combined with preventive maintenance practices, will enhance the reliability of the vehicle's battery management system, reducing the risk of future errors. Addressing this DTC promptly is crucial for maintaining optimal vehicle performance and ensuring the longevity of the electronic systems reliant on accurate battery information. Please like and subscribe to the channel. See you next time.